Institute of Aeronautical Engineering Autonomous. This is my tech talk. My name is N. Venkat Sai, rule number 23951802226, subject electric drives and static control, subject code AEE-D26. My topic is speed control of synchronous mission, department, electrical and electronics engineering. The crucial role of speed control in synchronous missions. Speed control is a cornerstone of synchronous mission operation, directly impacting performance, efficiency, and reliability across a vast array of applications. From industrial automation to power generation, precise speed regulation ensure optimal functionality and extends equipment lifespan. This presentation develops into the fundamental principles, historical methods, and cutting edge advancements in controlling the rotational speed of synchronous missions. Understanding this dynamic is essential for engineers and researchers working to enhance the capabilities of modern electrical systems. Understanding synchronous missions fundamentals. How they work. Synchronous missions are AC electrical missions that operates at a constant speed synchronized with the frequency of the power supply. Their fundamental operation relies on the interaction between a rotating magnetic field in the stator and a DC exciting magnetic field in the rotor stator. The stationary part containing windings they produce a rotating magnetic field when energized the AC current. Rotor. The rotating part with DC excited field winding creating a constant magnetic field that lock into the stator rotating field. Synchronous speed. The rotor rotates at precise same speed as the magnetic field generated by the stator determined frequency and the number of poles. These synchronized operations makes them ideal for applications requiring constant speed and precise frequency control, such as power generation and certain industrial drives. Traditional speed control methods, limitations and challenges. Historically, speed control of synchronous missions relied on mechanical adjustments or simple electrical schemes. While effective for some applications, these methods often came with significant limitations, particularly in terms of efficiency, precision, and dynamic response. Mechanical linkages using gears, belts, or other physical connections to adjust the load or prime mover speed. This method is often bulky, inefficient, and offers limited precision. Prime mover controller directly controlling the speed of the prime mover, example turbine governor, that drives the synchronous generators. This approach is effective for the power generation but less flexible for motor applications. Fixed frequency voltage operating directly from a utility grid where frequency and voltage are fixed, limiting speed control to discrete steps or requiring complex external mechanisms. These traditional methods frequently presented challenges such as high energy losses, slow response times, and an inability to adapt to varying load conditions, paving the way for more sophisticated electronic control solutions. Advanced control architectures exploring modern solutions. The advent of power electronics and digital signal processors have revolutionized synchronous mission speed control. Modern architectures offer unparalleled precision, dynamic response, and energy efficiency, overcoming the limitations of traditional methods. Vector control, field oriented control, separates the stator current into torque producing and flux producing components, allowing independent control similar to a DC machine. This enables highly dynamic and precise speed and torque regulations. Direct torque control, estimates torque and flux directly from stator voltage and current, then controls them by selecting optimal inverter switching states. Now for the fast torque response without need for complex coordinate transformations. Model predictive control uses a predictive model of the mission to optimize control actions over a future time horizon, considering constraints and minimizing a cost function, offers advanced handling of nonlinearities and disturbances. These advanced control strategies are essential for meeting the statement performance required of today's industrial and energy systems. Case study: high performance industrial applications. In high performance industrial applications such as rolling mills, exchangers, and advanced robotics, synchronous missions requires extremely precious and dynamic speed control to maintain product quality and operational efficiency. Precision manufacturing. In a modern rolling mill, synchronous motors with vector control ensure consistent sheets thickness and surface finish by preciously regulating roll speed. The rapid torque response minimizing deviations during sudden load changes. Crucial for high quantity mental productions. Robotics and automations. Synchronous servo motor, often employing advanced field oriented control algorithms, provide the accuracy and repeatability needed for robotic arms and automated assembly lines. Their ability to quickly accelerate, declare and hold positions in paramount for complex tasks. These applications highlight the crucial role of sophisticated speed control systems in achieving the demanding performance benchmarks of industrial automation. 0.1% of speed deviation tolerance in precision manufacturing process, 100 seconds response time, typical torque response required in high speed applications. Case study 2: renewable energy integration and grid stability. Synchronous missions play a pivotal role in renewable energy systems, particularly in large scale wind and hydropower generations. Effective speed control is crucial for integrating this variable source into the grid while maintaining stability and power quality. Wind power. Variable speed synchronization generation in wind turbines optimize power capture across different wind speeds. Advanced control adjusts rotor speed and pitch to maximize energy output and reduce mechanical stress. Hydroelectric plants. Synchronous generates in hydroelectric stations requires precious speed control to maintain grid frequency, especially during load changes or slanted operations. Governor systems works is traded with exciting control for stability. The integration of advanced speed control ensures that renewable energy sources contribute reliable and stable to the electrical grid, addressing the challenges of variability. Novel control algorithms enhancing precision and efficiency. Ongoing research is yielding novel control algorithms that push the boundaries of synchronization mission performances. These innovations focus on even greater precision, higher efficiency, and enhanced robustness against disturbances and uncertainties. Adaptive control algorithms that adjust their parameters in real time to compensate for changes in mission characteristics, load variations, or environmental conditions, ensuring optimal performances. Sensorless control techniques that estimate routers' positions and speed without physical sensors, reducing cost, complexity, and improving reliability, especially in harsh environmental. Sliding model control robust nonlinear control techniques that provide excellent disturbance rejections and fast dynamic response, particularly useful in systems with inherent uncertainties. These cutting edge algorithms are vital for unlocking the full potential of synchronous missions in future applications. Future trends and emerging techniques in speed control. The landscape of synchronous mission speed control is continually evolving, driven by demands for higher efficiency, greater integration with smart grids, and the electrification of new sectors. Several key trends and emerging technologies and shaping its future. Wide, wide bandgap semiconductors. Devices like SiC and GNA enable higher switching frequencies and efficiencies in power converters, leading to smaller, lighter, and more dynamic control systems. Digital twin technology, virtual model of physical missions coupled with real-time data, allowing for precise predictive control, optimization, and fault diagnosis, enhancing operational intelligence. Integrated smart grid solutions, synchronous missions control systems will become more interconnected, communicating with grid management platforms to provide demand response, frequency regulations, and voltage supports. Advanced materials, development of new magnetic materials and winding technologies will enable missions with higher power density and efficiency. Future challenging control systems to maximize their performances. This trend promises a future where synchronization missions are not only powerful but also intelligent, efficient, and seamlessly integrated into complex energy ecosystems. Conclusion. Key takeaway and future research directions. Speed control of synchronous missions has evolved dramatically, transforming for radical mechanical adjustments to sophisticated digital algorithms. This journey reflects continuous innovations aimed at enhancing precious efficiency and reliability across diverse applications. Key takeaways. Synchronous missions fundamentals underscore the inherent stability and constant speed operations. Traditional methods throw foundations faced limitations in dynamic performance and efficiency. Modern control architectures like vector control and DCT offers superior precision and responsiveness. Case studies demonstrate their critical role in both high-performance industrial process and renewable energy integrations. Novel algorithms and emerging technologies continue to push the boundaries of what's possible in control. Future researches, future development of AML driven adaptive and predictive control systems, integration of advanced sensorless control techniques for cost reduction and reliability, optimizing control for wide bandgap power electronics to achieve even higher efficiencies, enhancing reliances and cybersecurity in networked control system for smart grids, exploring new control paradigms for mission utilized advanced materials for extreme conditions. The field continues to be a fertile ground for researches and developments, promising even more robust efficiency and intelligent synchronous missions applications in the year to come. Thank you.